do these definitions quickly. Hello and welcome back to Calculus 2, section 6.8. We are going to redefine our logarithmic and exponential functions in terms of calculus. You learned before that these exponential functions are functions that have the base and then the variable is in exponent, therefore exponential function. You know they grow fast, and you know that you do the whole spiel of problems in medical field, engineering field, also history, right, for carbon dating. You also have a whole bunch of economics, right, considerate, like talking about the loans and interest and all that kind of stuff. So technically, logarithmic and exponential functions cover all areas of human endeavor. Technically, anything we do is going to involve them in some way. We also understand that, you know, the earthquakes and waves and all of these kind of things in terms of logarithmic stuff. So pH in chemistry, right, has log, so base 10. So now, what are these ideas in terms of calculus? We start with the logarithmic one. So the natural logarithm ln is defined by ln x is equal to the integral 1 to x of 1 over t dt. Observe that the dummy variable u is t, which changes into x when you plug in the limits. If you are to solve this integral, right, there's a little proof over here, even though it's not a proof class, but we can do it. This is going to be ln of t, absolute t, right, computed from 1 to x, which gives you ln x minus ln 1, which is just ln x. And we are considering this for all x is larger than 0. One thing that I want to outline for you is this use of absolute value. You know that, well, you were supposed to learn that the integral of 1 over x dx is ln absolute x plus z. And why absolute x? Well, if you consider the domain of the input function, if you draw the input function, you are going to see something like this, whose domain is from negative infinity to 0, union 0 to positive infinity. And if you consider the domain of just ln x, whose graph looks like this, clearly the domain is just 0 to infinity. Now you can have a mathematical operator that changes one function into another function and kills half of its domain. Because imagine that your limits of integration, which would be perfectly valid to have on this side, because function is 1 over x, to have limits of integration negative 3 to negative 1, without absolute value, negative 3 to negative 1 would not be computable in a situation like this at all. So it will be this paradox where you're able to pose the question, but you're not able to do it. So this absolute value is not there for decoration. What absolute value does is introduces another branch over here, and then your domain is matching the domain before you apply the integral. So absolute value on that ln x is not there for decoration. It actually allows you to have the graph whose domain matches the domain of the input, and you have satisfied that. So I just wanted to put that aside so you know. What follows in the lecture are the proofs where you can use your this new definition to show how the formulas work, such as ln xy is ln x plus ln y. ln x over y is ln x minus ln y, and ln x to the p is p ln x. These are the three basic properties of logs, and they can be proven by using the definition up there. Again, it's in our honors section if you're interested to see these proofs. I mean, obviously open the book, but also you can stop by my office hours and we can talk about it. The one that is really quick and interesting to see is the fact that ln of 1 is equal to 0, right? So that's the one that it's really cute, because I can, you know, when we solve this side, you get the integral of 1 to 1, right? And we know from Calc 1 that integral 1 to 1 is 0 because it has 0 width. There's no area there. So this would eventually translate into, you know, ln x was the integral 1 to x of 1 over t dt. If you want to compute ln of 1, then that's integral 1 to 1 of 1 over t dt, which is equal to 0, because 1 to 1 we have that theorem in Calculus 1. That's a really cool calculation. So there are a lot of you know, these nice little cute proofs that you can do to get this. The interesting examples here, which are going to show up a lot in Chapter 7, would be these integrals where you get to use u substitution to transform those integrals into ln answers, right? So say you have x over x squared minus 9 dx. So in this situation, we at this point we only know u sub, right? So that would be a natural thing to do. U equals x squared minus 9, du equals 2x dx. Note that you already have x dx, you are missing a 2. So 2 1/2 will be added to the integral, and the entire integral changes into 1/2 1 over u du, which is 1/2 ln absolute u plus c. We go back to x variable because the problem was posed in x. So be mindful of these. Obviously, solve all of these on your homework to be very comfortable with this, because partial fraction decomposition is coming, right? Should I say the winter is coming? Because it is. It's September, and the next one is the October, so it's approaching. The next one is the calculus definition of number e. That special number. So number e satisfies ln e is equal to 1 to e 1 over t dt, which is equal to 1. So we define the function ln x first, and then in the same fashion I earlier plugged in 1, now we're going to plug in e. And e is this transcendental number which produces 1 in this calculation. Now, there is another calculus definition for number e, which you need to know from your Calculus 1, which is the limit definition. So I'll put or limit n goes to infinity 1 plus 1 over n to the n is equal to e. So that definition also needs to be noted, and that definition is also calculus, right, because it's based on the limit. The next definition is definition for exponential function e to the x, which is defined as the inverse of log. So see, it's completely backwards than what you learned in PreCalc. In PreCalc, you learn exponential, and then you define log as the inverse of exponential. And now in Calculus 2, we define the log function in terms of that integral, and then we define exponential function as the inverse of the log. So now I will say that the exponential function y equals e to the x is inverse of x equals ln of y. And we know that we can define ln of y because we have the definition, right? So I can write ln of y is equal to integral 1 to y of 1 over t dt. So we define ln, then we define number e in terms of that ln, and then we can define the exponential function and the inverse of the logarithmic function. And then again, in terms of all of those properties and rules and everything, you can do proofs for each one of the properties of exponential functions, right? I will not waste your time. All of this stuff is listed in the textbook, so you will look it up. It says e to the x plus y is e to the x times e to the y. E to the x minus y is e to the x over e to the y. And I'll just put 3 dots because there are 5 of these rules. I wrote only 2 out of 5. Those should be on your class prep, and all of these are algebraic rules that you learned. We do not introduce anything new. What my focus is supposed to be here is at derivatives. And I understand that I will probably go 2-3 minutes over time, but I really need to make sure that you know what I call boss equations. So when you are talking about the derivative of e to the x, you just know it's e to the x, and that's the end of the story. But then e is not the only base that you can have in exponential function. What do you do if you have 5 to the x, right? So the derivative of any base raised to the x is going to be, again, a to the x times ln a. Now, this formula tends to be the more general case because it allows for any base. But that's still not the major formula, because the major formula would allow for also any function to be in the exponent, not just function x. Remember, y equal x is just a linear function that's 45 degrees, right, straight line to the origin. Can we have x squared? Can we have sine x? And the answer is hell yes. So in that case, we will be using the chain rule, and that will give us what I call the boss equation. Then I need to go through logs and we're done. The boss equation would be a raised to any function. So now you can see that e to the x is reflected in this formula because a is e and f of x would be just x. But then you have the freedom to have 7 to sine x, and that works as well. So the derivative of something like this would be a to f of x times the derivative of x, which is the chain rule, times ln a because of the base. And this is what I call the boss equation for differentiating exponentials, because this is the most general case that we can have. Again, if a is e and f of x is x, then a is e, f of x is x, times the derivative of f of x is 1, times the ln of e is 1, and here is your derivative of e to the x is e to the x, even if you use this formula. So this is the most general case that you can run into using having different derivatives of the exponential functions. The next creature would be ln, right? So we start by, again, just working on the basic ln x. And you all memorize that you are working with just ln x. I believe this is all in the textbook somewhere. Yeah. So you have the derivative of this thing. Now again, ln x is actually log base e of x. That's the definition for ln x. It's just the basic logarithmic function, but it's a specific base, so we gave it a specific name and a specific thing. So now I say, well, what if I have a different base? So what if the base is not e, so it's ln? What if the base is 7 or 13 or 1/2? In that case, we would have the derivative of log of any base of x, and that would be still 1 over x. But now I have to multiply by ln a. Divide by ln a in denominator. And the last thing that we need to do is to say, well, I want the boss equation, because function doesn't have to be just y equal x. It could be x squared, it could be sine x, it could be anything else. So this is where I write the boss equation now. The derivative of the log of any base of any function is going to be the derivative of the function divided by the function times ln a. And now this formula will take the derivative of anything with let me just fix this thing here. There we go, ln a. And again, all of these formulas would reduce back to basic ln's and so on. Examples for this are very simple. You just, plug and chug. I'll do one example for log real quick. Log base 6 of x cubed is going to be, the derivative is 3x squared divided by x cubed times ln 6. And then these guys cancel, so it's 3 over x ln 6 for this problem. It's extremely quick, and that's all it is. So just follow your nose. Next class, 6.9, a lot of word problems, and we are going to do some of the lab time next class for at least an hour. So make sure you do as much as you can on your lab 1 to bring it in, and try this stuff, fix it, and work on it. See you all in 5 days, or sooner if you stop by for office hours. And ciao for the stream.